These are the 7 separate, independently measured ways Mars is actively working against anyone who eventually lands on it, and why the planet we've been dreaming about for 60 years turns out to be far more dangerous, in far more specific and quantifiable ways than the postcard images from NASA ever let on. This is the full picture of Mars hostility, built entirely from data gathered by rovers, landers, and orbiters that have actually been there, from the radiation numbers measured by Curiosity to the dust storm that ended a rover's 15-year life in a matter of days. If you're new here, go ahead and hit like and subscribe, and drop a comment telling me where you're watching from and what you're doing right now, because I genuinely love seeing who's out there listening. Now let's get into it. Before we get into the specifics, it's worth laying out exactly what we're actually going to cover, because Mars doesn't just have one problem, it has an entire stack of them, layered on top of each other, and each one has been directly measured by real hardware that's actually been there. We're going to start with radiation, the invisible one, the one you can't feel happening to you in the moment. From there we'll move to the dust storms, including the exact one that ended the career of one of the most successful machines humanity has ever sent to another world. After that we'll get into the ground itself, the chemically active soil that turns actively dangerous the moment sunlight hits it. Then we'll talk about the air, or the almost complete lack of it, and the temperature swings that come with having almost no atmosphere to hold on to heat. After that, we'll get into what all of this does to the human body specifically, the bones, the muscles, the long-term physical cost of simply existing in a gravity field that's little more than a third of what we evolved with. Then we'll look at the 60-plus-year history of actually trying to send machines there in the first place, a history with a real, well-earned nickname among the people who work in this field. And then, at the end, we'll get into the part of this story that complicates everything we've just covered, a discovery that's only fully come together in the last couple of years, buried in seismic data collected by a lander that finished its mission back in 2022. Every single piece of this is built from measured data, not speculation, and by the time we get through all of it, you'll have a genuinely complete, ground truth picture of why this planet is so much harder to deal with than the postcard images ever suggested. Let's start with the very first one, the invisible one, because it's the danger you can't see, can't feel, and can't avoid just by wearing a thicker jacket: radiation. Earth has 2 enormous advantages that most of us never think about because we've never lived without them. The first is a global magnetic field generated deep in our planet's molten core, which deflects the bulk of the charged particles streaming at us from the sun and from deep space. The second is a thick atmosphere, roughly 100 kilometers of air stacked above our heads, which absorbs even more of what the magnetic field lets through. Mars has neither of these things in any meaningful sense. It lost its global magnetic field billions of years ago, and what atmosphere it has left is only about 1% as thick as ours. That combination means the surface of Mars is essentially standing out in the open, exposed to a stream of galactic cosmic rays and solar energetic particles that Earth's surface never has to deal with. We're not guessing about how bad this is anymore, because we've actually measured it. NASA's Curiosity rover carries an instrument called the Radiation Assessment Detector, RAD for short, and it has been quietly logging radiation data on the Martian surface since it landed in August of 2012. That's over a decade of continuous measurement, through different seasons, through solar storms, through the day-to-day rhythm of a planet that has no idea it's being watched this closely. What RAD found is that a person standing on the surface of Mars would absorb an average of about 0.7 millisieverts of radiation every single day. To put that number somewhere you can actually picture it, astronauts living aboard the International Space Station take on somewhere between 0.4 and 1 millisievert per day. So the surface of Mars, according to the people who actually built and ran this instrument, sits in roughly the same radiation ballpark as low Earth orbit. That's already a strange thing to sit with. We tend to think of the International Space Station as an extreme environment, a place astronauts train for years to survive, and yet standing on the actual ground of another planet exposes you to a similar dose. But the surface dose is only part of the story, and it's arguably not even the worst part. Getting to Mars and back is its own radiation gauntlet. During the roughly 8-month cruise phase, when a spacecraft is out in open space, with nothing but its hull between the crew and the cosmos. RAD measured an average galactic cosmic ray dose rate of about 1.8 millisieverts per day. Stop and sit with that figure for a second, because it's a big one. On Earth, the average person absorbs about 2 millisieverts of background radiation across an entire year, from the ground, from the air, from cosmic rays that do make it through our shielding, from the food we eat. In deep space, on the way to Mars, you are absorbing roughly that same yearly dose every single day of the trip. Now put the whole mission together the way researchers who study this have modeled it. A round trip to Mars looks something like this, about 180 days getting there, somewhere between 500 and 600 days actually on the surface doing the work the mission was sent to do, and then another 180 days coming home. When you add up the radiation exposure across that entire journey, you land on a cumulative dose of somewhere around 1 to 1.1 sieverts, depending on exactly how long the surface stay runs. That number matters because space agencies actually have hard limits on how much radiation an astronaut is allowed to absorb over an entire career, and this single mission would use up almost all of it in one trip. The European Space Agency generally sets its career limit at 1 sievert, a threshold tied to roughly a 5% increase in lifetime fatal cancer risk. A single Mars mission, on the numbers we just walked through, sits right at that ceiling, maybe slightly over it, depending on how long the astronauts stay. NASA's own standard is even stricter. NASA caps the acceptable increase in an astronaut's excess cancer risk at 3%, a number that was designed with missions to low Earth orbit in mind, long before anyone was seriously planning to send a crew 400 million kilometers away for years at a time. Because of that mismatch, NASA has actually been working with the National Academy's Institute of Medicine to figure out what an appropriate radiation limit even looks like for a mission this long, this far from home, and this far outside the kind of spaceflight the original standards were written for. It's worth pointing out that the people who actually run this instrument don't sound panicked about it. Don Hassler, the principal investigator for RAD at the Southwest Research Institute, presented these findings back in December of 2013 at a meeting of the American Geophysical Union, and his read on the numbers was that the mission dose is, in his words, certainly a manageable number. He noted that the rough career limit for an astronaut sits around 1 sievert, and that a Mars mission comes in close to that line without necessarily blowing past it in some catastrophic way. That's an important piece of nuance, because this isn't a story about radiation levels that make Mars flatly impossible to visit. It's a story about a planet that offers essentially no margin for error on a problem most of us never have to think about here on Earth. And radiation on Mars doesn't arrive as a smooth, predictable trickle. It spikes. RAD recorded a hard solar energetic particle event on what mission planners call Sol 242, which corresponds to April 12th and 13th of 2013 in Earth time, and that event produced a sharp jump in the measured dose rate. Alongside events like that, RAD also picked up something called Forbush decreases, which are temporary dips in the background cosmic ray flux caused by interplanetary coronal mass ejections, essentially bursts of solar material that act like a magnetic umbrella for a little while, briefly shielding the surface before the radiation levels climb back to normal. What all of this tells us is that the Martian radiation environment isn't a flat, steady hum in the background. It's a genuinely active system, tied to the Sun's own 11-year activity cycle, capable of throwing sudden spikes at anything standing on the ground below. There's also a very specific, very useful number buried in the RAD dataset that's worth mentioning, because it shows how much our predictions were off before we actually went and measured this directly. The published surface dose rate from RAD works out to about 76 milligray per year. Before Curiosity landed, scientists had made educated guesses about what this number would be, and those guesses were all over the map. Some models assumed something like 150 milligray per year, more than double what RAD actually measured. Other models assumed something closer to 50 milligray per year, plus or minus 5, undershooting the real figure. The truth landed in between those two competing predictions, which is a small but telling reminder that even the smartest people working with the best available physics can be wrong by a factor of 2 in either direction when the planet in question is one nobody has ever actually stood on with an instrument in hand. So what does all of this actually mean for a human being trying to live on Mars, rather than just visit briefly and leave? According to researchers looking at long-duration exposure, 3 consecutive years on the Martian surface would be enough, on its own, to exceed a NASA astronaut's entire career radiation limit. 3 years. Not a lifetime of repeated missions, not decades of exposure. 3 years standing on a planet with no magnetic field and barely any atmosphere would use up the same radiation budget that's currently supposed to last an astronaut their whole working life. That's the kind of number that reframes the entire conversation about what living on Mars, as opposed to briefly visiting it, would actually cost the human body. It's worth sitting with why NASA and the European Space Agency even ended up with 2 different numbers in the first place, because it isn't arbitrary. NASA's 3% excess cancer risk standard was built around the idea of managing risk relative to an individual astronaut's overall lifetime cancer odds, which naturally means the specific radiation dose that trips that threshold varies somewhat from person to person, depending on factors like age and sex, since baseline cancer risk itself varies across a population. ESA's flat 1 sievert limit is a simpler, more uniform threshold, easier to communicate and plan missions around, but less finely tuned to any individual crew member's actual risk profile. Neither approach is simply right or wrong. They're 2 different philosophies, developed by 2 different agencies working from the same underlying body of research, for translating the same genuine scientific uncertainty about long-term radiation exposure into an actual, workable operational limit that mission planners on both sides of the Atlantic can design real hardware and real mission timelines around. And a Mars mission, sitting right around that 1 sievert line depending on exactly how long the surface stay runs, is precisely the kind of mission where which standard you happen to be using can be the difference between a mission that's approved to fly and one that isn't. None of this means radiation is some unsolvable deal-breaker. Engineers already talk about shielding strategies, thicker habitat walls, burying structures under Martian regolith, using water as a radiation buffer, since water happens to be excellent at absorbing charged particles. But every one of those solutions is a workaround for a fundamental fact about this planet. It does not protect you the way Earth does, not even close, and every single person who eventually sets foot there is going to be carrying that invisible cost with them the entire time, whether they can feel it happening or not. It helps to slow down for a second and really think about why this problem exists in the first place, because it's easy to hear numbers like sieverts and millisieverts and let them wash past you without actually landing. Every living thing on Earth evolved underneath 2 enormous, invisible shields, and neither of them was ever a choice we made. The magnetic field came from the churning of molten iron deep in our planet's core, a process that's been running for billions of years, long before anything resembling life existed to benefit from it. The atmosphere came from a mix of volcanic outgassing and later, the activity of living things themselves, building up over an equally long stretch of time. Together, those 2 things did such a thorough job of protecting the surface that human beings never had to develop any biological defense against cosmic radiation at all. Our bodies simply never needed one. Every organism that's ever lived on the surface of this planet got to skip that particular evolutionary arms race entirely, because the shielding was already there before life even started. Step off that shielded surface, and none of that protection comes with you. That's true the moment an astronaut leaves Earth's atmosphere, and it stays true for the entire rest of the trip, all the way to Mars and all the way back. It's worth separating out the 2 different sources of radiation that RAD has been tracking, because they behave differently and they matter for different reasons. Galactic cosmic rays are the steady background hum, high-energy particles that originate from outside our solar system entirely, likely from ancient supernova explosions and other extreme events happening across the galaxy over millions of years. They arrive at a fairly constant rate, modulated slowly by the Sun's own 11-year activity cycle. Solar energetic particles are the other category, and they're the more dramatic, unpredictable one, bursts of high-energy particles thrown out directly by the Sun during solar flares and coronal mass ejections. Those can spike radiation levels sharply and quickly, the way RAD recorded during that hard event back on Sol 242 in April of 2013. A future Mars mission has to be engineered to handle both of these at once. the slow, grinding, always present background dose from galactic cosmic rays, and the sudden, unpredictable spikes from solar activity that could arrive with very little warning. There's also something worth noticing in how the numbers actually broke down once RAD started sending back real measurements, because it's a good reminder of how much guesswork was involved before anyone actually went and checked. Remember, one set of pre-Curiosity models predicted a surface dose rate around 150 mg per year, more than double what RAD ultimately measured. A different set of models predicted something close to 50 mg per year. The real number, 76 mg per year, landed almost exactly between those two competing estimates. That's not a small detail. It means that even within the community of scientists who specialize in exactly this kind of prediction, working with the best physics available at the time, educated guesses about Mars's radiation environment were off by roughly a factor of 2 in either direction, purely because nobody had ever actually measured it directly before. It's a useful thing to keep in mind anytime you hear confident predictions about what some part of Mars is going to be like, because history keeps showing that actually landing an instrument there and measuring the real thing tends to move the number substantially, sometimes in ways that make things better than expected, and sometimes worse. That's radiation. Now let's talk about the thing that actually killed a spacecraft in real time, in front of the entire world, over the course of a few brutal weeks in the summer of 2018. Dust storms on Mars are not like dust storms on Earth. On Earth, even the worst haboob rolling across a desert is a local, survivable, temporary inconvenience. On Mars, a dust storm can grow to cover the entire planet at once, blotting out the sun across every square kilometer of the surface simultaneously, and it can stay that way for months. The 2018 event is the clearest case study we have, because we watched it happen in close to real time, through the eyes of multiple spacecraft at once. It started small. On May 30th, 2018, NASA's Mars Reconnaissance Orbiter spotted a regional dust storm forming, nothing that looked catastrophic at first glance. But this storm didn't behave like the regional storms that had come before it. By the second week of June, it had grown to cover a full quarter of the planet. By June 13th, it had expanded far enough to reach the Curiosity rover, which was operating in Gale Crater on the completely opposite side of Mars from where the storm began. And on June 20th, NASA made the announcement that the storm had done something almost unimaginable. It had grown to cover the entire planet, every region, all at once. Scientists measure how much sunlight a dust storm blocks using something called optical depth, represented by the Greek letter tau. It's a simple enough concept. The higher the tau value, the less sunlight makes it down to the surface. A tau of 1 already blocks about 63% of incoming sunlight, which on its own would be a serious problem for anything trying to run on solar power. During the 2018 storm, the global tau reached a value of 5, with local peaks hitting 10 or even higher. At the specific location where NASA's Opportunity rover was working, the tau at the peak of the storm reportedly hit 10.8. Multiple sources described the resulting darkness in almost the same way, using the same simple, blunt comparison. It turned day into night. That phrase isn't just poetic exaggeration for a press release. NASA project manager John Callis described the sky during the storm in language that makes the scale of it clear. The skies, he said, were incredibly dark, to the point where no sunlight gets through. It's nighttime during the day. Think about that for a second. Not a grey, gloomy, overcast afternoon. Actual, functional nighttime, in the middle of what should have been the Martian day, because the dust in the atmosphere was thick enough to fully block the sun. For a rover running on batteries and solar panels, that kind of darkness isn't an inconvenience, it's an execution. Opportunity had been exploring Mars since landing in Meridiani Planum on January 25, 2004, and by 2018, it had already blown past every reasonable expectation anyone had for it. It was designed for a 90 Martian day mission. It ended up operating for 5,111 sols, which works out to roughly 14 years and 138 days on Earth's calendar. NASA's own mission page puts it plainly. The rover exceeded its life expectancy by a factor of 60. 60 times longer than engineers ever expected it to last, on a planet that was actively trying to kill it the entire time. And then, on June 10, 2018, in the middle of the growing storm, Opportunity sent its last transmission. It wasn't a dramatic farewell message. It was a routine data dump, the kind of unremarkable status update the rover had sent thousands of times before. Power levels, atmospheric readings, the ordinary bookkeeping of a working machine. Nobody on the mission team knew, in that exact moment, that it would be the last time they heard from it. The dust storm had cut off enough sunlight that Opportunity's solar panels couldn't generate meaningful power anymore. Its batteries drained, and without power, its internal heaters shut down too, which meant the electronics inside were suddenly exposed to Martian nighttime cold, with no way to protect themselves. What followed was months of waiting and trying. NASA sent more than 1,000 separate recovery commands to the rover after that last transmission, each one an attempt to coax some kind of response out of a machine that had gone completely silent. Engineers specifically timed some of these attempts around the seasonal windy periods that Mars typically produces in the months after a storm clears, because Opportunity had actually been saved by wind before. Earlier in its mission, gusts and dust devils had repeatedly blown accumulated dust off its solar panels by accident, cleaning them just enough to keep the rover charged and functioning long past what anyone expected. It's part of the reason Opportunity lasted 60 times longer than planned in the first place. This time, the wind never delivered the same rescue. On February 13, 2019, after months of silence and a final unsuccessful attempt to reach the rover, NASA formally declared the mission over. There's something almost eerie about where Opportunity ended up. It's still there, on the western rim of a place called Endeavour Crater, in a location named Perseverance Valley, exactly where it stopped moving back in June of 2018. It hasn't gone anywhere since, and it isn't going anywhere. And here's the detail that sits strangely with a lot of people once they hear it. Some of the dust that killed it has, over the years since, partially blown off its solar panels again, the same natural cleaning process that saved it so many times before. If a future mission ever reached it, dusted it off, and replaced its batteries, there's a real possibility the same rover, sitting untouched on Mars for years, could work again. So why does dust do this much damage in the first place? Part of the answer is that Martian dust isn't like dust on Earth. It's extremely fine, powdery material, closer in texture to flour than to sand, and it carries a mild electrostatic charge. That charge is part of why it clings to surfaces the way it does, sticking through static attraction rather than simply settling under gravity the way heavier particles would. And once it settles, there's nothing on Mars to wash it away. There's essentially no rain. On Earth, a good storm rinses dust and grime off almost everything eventually. On Mars, once dust lands on a solar panel or a piece of equipment, it stays there indefinitely, unless wind physically moves it somewhere else. This is exactly why dust devils, those small spinning whirlwinds you sometimes see in NASA's Mars photography, became such a critical, almost lucky factor in these rover missions. They're not the storms themselves. They're smaller, localized events, caused by solar heating creating convective updrafts, and they occasionally passed directly over rovers and swept the accumulated dust straight off their solar panels. That accidental cleaning is a huge part of the reason Spirit and Opportunity both operated for years longer than their designed lifespans. But dust devils are unpredictable. You cannot plan a mission around hoping one shows up in the right place at the right time, and during an actual global storm, with dust falling from every direction at once, there's simply more dust arriving than any dust devil could realistically clear. There's also a communication cost to all of this that's easy to overlook. Airborne dust doesn't just block sunlight, it also scatters and absorbs radio signals. So during a storm like the 2018 event, a spacecraft's ability to transmit a clean signal back to Earth can weaken at exactly the moment when engineers most need reliable data to understand what's happening to it. It's a cruel kind of compounding problem. The storm that's draining your power is, at the same time, making it harder for you to even call home and say so. Scientists have also studied what Martian dust is actually made of, and the picture that emerges connects back to the planet's own violent geological history. Measurements from the Mars exploration rovers found the dust is notably rich in sulfur and chlorine, elements that show up heavily in two very different kinds of material. Evaporite minerals, the kind of salty residue left behind when ancient lakes dried up, and volcanic ash. One particular region of Mars, called the Medusa Fossae Formation, is considered a major source of this material. It's an enormous deposit sitting downwind of the planet's largest volcanoes, and it's so fine-grained and low-density that radar astronomers gave it its own nickname, stealth, because it barely reflects radio signals bounced off it from telescopes on Earth. Somewhere in that combination of ancient volcanic activity and long-vanished lakes is the source of the very same dust that ended a rover's 14-year mission in a matter of weeks. Dust isn't only a threat during the dramatic, headline-making global storms either. It's a constant, grinding, mechanical wear problem, even on an ordinary day. Curiosity, the rover we spent so much time on earlier for its radiation measurements, ran into its own dust-related mechanical crisis in December of 2016, when its rock-sampling drill developed a fault in the feed mechanism that was supposed to advance the drill bit forward into rock. The problem stopped drilling operations entirely for over a year, until engineers back on Earth worked out an entirely new technique, nicknamed feed-extended drilling, where the bit stays locked in an extended position and gets pushed into the rock using the motion of the rover's whole robotic arm instead of the internal feed mechanism that had failed. It's a small story compared to something like the loss of opportunity, but it's a useful reminder that Mars doesn't need a headline-grabbing global storm to cause real, mission-threatening problems. Sometimes it's simply the slow, unglamorous wear of operating complex mechanical systems, day after day, on a planet whose environment was never designed with any of our machinery in mind, that ends up being the thing engineers have to fight against. Global dust storms like the one in 2018 aren't unique, one-time events either. They're part of the planet's ongoing weather pattern, tied to the way sunlight heats bare regolith unevenly across the surface and creates the thermal contrasts that fuel bigger and bigger storms. Mars has thrown up regional storms plenty of times throughout the history of rover missions there. It's the fully global ones, the kind that swallow the entire planet at once, that represent the real worst-case scenario. And Opportunity's story is the clearest proof we have of exactly what that worst case looks like when it actually happens to a working spacecraft. Which brings up an obvious question for anyone thinking seriously about sending people to Mars, not just robots. A rover going silent is a tragedy for the mission team that built it and loved it. But it isn't a life-or-death emergency in the way the same scenario would be for a human crew relying on solar power for life support, for heating, for the systems keeping breathable air circulating inside a habitat. Whatever engineering solutions eventually get built for crewed Mars missions, they're going to have to account for a storm that can block the sun across the entire planet, all at once, for weeks or months at a time, because we've already watched exactly that happen, and we've already watched exactly what it can do to a machine that wasn't ready for it. It's worth pausing on the sheer speed of what happened in 2018, because that's honestly one of the most unsettling parts of the whole event. This wasn't a slow-building crisis that gave engineers weeks to plan around it. On May 30th, it was a regional disturbance, the kind of thing the mission team had watched Mars produce plenty of times before, without much drama. Within about 2 weeks, it had grown to cover a quarter of the entire planet. Within about 3 weeks of that first detection, it had grown to cover all of it, every region, simultaneously. Think about the scale of that kind of growth rate applied to a planet roughly half the diameter of Earth, but still enormous by any human standard. A storm expanding fast enough to swallow an entire world in less time than it takes most of us to finish a single work project. And there was nothing anyone on Earth could do about it, except watch the data come in, and hope the hardware they'd already built and already sent, tens of millions of miles away, was tough enough to survive whatever was coming. The team running Opportunity had actually been through smaller versions of this exact nightmare before, which makes the ending even more poignant in a strange way. Back in 2007, severe dust storms had already pushed Opportunity to the edge once. By July 18th of that year, the rover's solar panels were reporting power at just 128 watt-hours, the lowest level either rover had recorded up to that point. NASA suspended all science activities for Opportunity indefinitely, while the team waited the storm out. After about 6 weeks, the 2007 storm finally abated, and Opportunity recovered and kept going, eventually reaching a crater called Victoria and spending nearly a year exploring inside it. So by the time 2018 rolled around, this wasn't unfamiliar territory for the mission team. They'd survived a serious dust crisis before. They knew, in theory, what a bad storm looked like and how their rover tended to respond to one. What made 2018 different wasn't a lack of experience. It was scale. The 2018 storm simply didn't behave like anything that had come before it, and this time, waiting it out wasn't enough. There's a particularly haunting detail buried in how Opportunity's mission actually ended, one that's easy to miss if you only hear the broad outline of the story. The rover's very last transmission wasn't corrupted or incomplete in some way that hinted at catastrophe. It was ordinary. It was the kind of routine engineering data the rover had sent back thousands of times across 14 years. Power levels, some atmospheric readings, the unglamorous bookkeeping that keeps a mission running day to day. Nobody on the team had any way of knowing, in that specific moment, that they were reading the last message a machine they'd worked with for over a decade would ever send. There was no dramatic final image, no last-second warning, just an ordinary status update, and then, after that, nothing at all, for months, no matter how many times NASA reached back out. And reach out they did, again and again, in a sustained effort that says something about how much this specific machine meant to the people who built and operated it. More than 1,000 separate recovery commands sent over the following months, each one essentially a message in a bottle thrown at a rover that had gone completely dark. Some of those attempts were deliberately timed to coincide with the windy season NASA expected in the months following the storm, precisely because wind and the accidental cleaning it sometimes provides had already saved this exact rover multiple times earlier in its mission. There's something almost human about that persistence, engineers refusing to give up on a machine because it had proven, over and over across 14 years, that it was capable of surprising everyone who thought they understood its limits. By the time NASA finally made the call, on February 13, 2019, declaring the mission over after one final unanswered attempt, Opportunity had already rewritten what anyone thought a solar-powered rover on Mars could accomplish. Designed to last 90 Martian days, built to travel about 1,100 yards. It ended up operating for over 5,000 sols and covering more than 28 miles of Martian terrain, a distance that, back in July of 2014, had already let it break the off-world driving distance record previously held by the Soviet Union's Lunokhod 2 rover on the Moon. It had explored Victoria Crater for the better part of a year. It had reached Endeavour Crater and kept working there for years more. By early 2018, before the storm even started, it had already sent back over 224,000 individual pictures. The 2018 storm didn't just end a mission. It ended one of the most successful pieces of exploration hardware humanity has ever built. And it did it in a matter of weeks, after that same hardware had spent nearly a decade and a half quietly proving just how tough it actually was. Let's move from the sky down to the ground itself, because even if you somehow solved radiation and somehow rode out every dust storm, the very soil under your boots on Mars is working against you. The culprit here is a group of chemical compounds called perchlorates, and they're not some obscure, rare trace element. They're everywhere. Perchlorates were first detected on Mars all the way back in 1976 by NASA's twin Viking landers, the earliest successful missions to actually touch down on the planet's surface. For decades, that early detection sat there as an interesting data point. Then, in 2009, NASA's Phoenix lander confirmed it again directly, finding that perchlorates make up somewhere between 0.4 and 0.6% of the soil sample it collected. Other research looking at the broader picture across the planet puts the range even higher, somewhere between 0.5 and 1% of the soil by weight. Those percentages might sound small if you're not used to thinking about toxicology, but they're not small at all. Perchlorates are toxic to humans, specifically because of what they do to the thyroid gland. They interfere with the thyroid's ability to take up iodine, which in turn disrupts the production of thyroid hormones that regulate an enormous range of processes in the human body, and the danger is especially serious when it comes to fetal development. This isn't a fringe concern raised by one lone researcher either. It's been confirmed repeatedly by scientists working directly with NASA and the European Space Agency, people who have spent their careers thinking specifically about what it would take to keep humans alive on this planet. Chris McKay, a scientist at NASA's Ames Research Center, put it about as directly as it can be put. It's bad for astronauts, he said, because it is toxic for humans. as it interferes with the thyroid. Peter Smith, who served as principal investigator on the Phoenix lander mission that confirmed these compounds in the Martian soil, was even blunter about the scale of the problem. At 0.5%, he said, that's a huge amount. Very small amounts are considered toxic, so you'd better have a plan to deal with the poisons on the surface. This is a person who spent years of his professional life studying this exact soil, telling anyone who would listen that it needs to be treated as a genuine hazard, not a footnote. And it gets worse once you factor in what Mars does to perchlorates once they're already sitting there. The planet's surface is bathed in high levels of UVB and UVC radiation, the more dangerous bands of ultraviolet light that Earth's surface is almost entirely protected from, thanks to our ozone layer. Mars doesn't have an ozone layer worth mentioning. When that intense ultraviolet light hits perchlorates already present in the soil, it can convert them into even more reactive and dangerous byproducts, compounds called hypochlorite and chlorite. Laboratory tests have shown these UV-activated byproducts are so aggressive that they can kill even bacteria that had previously shown some tolerance for perchlorates on their own, and researchers studying corrosion have flagged them as a potential threat to metal components as well, not just biology. That laboratory finding lines up with a broader, more unsettling picture that's emerged from more recent research. A study published in 2017 found that certain compounds present in Martian soil, combined with realistic surface conditions, including that ultraviolet exposure, could wipe out entire bacterial cultures within minutes in controlled lab tests. Minutes, not days of slow decline, not gradual die-off, but a near-total kill within a very short window. That result has real implications for how scientists think about the search for life on Mars, but it also reframes what the surface itself represents for any future human visitors. Not just an inhospitable environment, but potentially something closer to a mild sterilizing agent, actively hostile to biology, in a way most deserts on Earth simply are not. There's direct evidence about what this kind of material could do to human lungs too, and it doesn't come from speculation. It comes from an actual laboratory study, cited in research examining the health risks astronauts would face on Mars, where scientists exposed lab mice to Martian soil simulant at 2 different dose levels, a low dose of 0.1 milligrams per mouse and a higher dose of 1 milligram per mouse. When researchers examined the animals just 7 days after exposure, they found mild fibrosis, meaning scarring, scattered throughout the lung tissue, along with immune cells that had become laden with the inhaled particles as the body tried to deal with the foreign material. That's from a simulant, a stand-in material, designed to approximate the real thing, at doses that are, relatively speaking, tiny. It's a preview of what fine, chemically hostile Martian dust could do if it worked its way into human lungs over the course of a long-duration mission, particularly given how notoriously difficult this kind of ultra-fine, electrostatically clingy dust is to keep out of habitat seals, air systems, and eventually, spacesuits. To be fair to the full picture, there is a more optimistic strand of research running alongside all of this. Some scientists studying the problem argue that the actual health risk from perchlorates could be manageable with the right engineering, because filtration systems, if properly designed, might be sufficient to strip enough perchlorate out of processed dust and air to bring the risk down to something workable for a human crew. And there's an interesting twist buried in the chemistry too. Perchlorate isn't purely bad news. It's also being seriously studied as a potential resource, something that could theoretically be broken down chemically to extract oxygen, which is obviously an incredibly valuable thing to be able to produce locally on a planet where you can't just breathe the air outside. So the same compound that's toxic enough to demand real caution is also, chemically speaking, a possible piece of the puzzle for making Mars survivable in the long run, which is a strange kind of contradiction, but it's exactly the kind of contradiction that keeps showing up over and over again once you actually dig into how this planet works. Either way, what's not in dispute is this. The ground itself on Mars is not neutral. It's not simply barren, inert dirt waiting for someone to plant a flag in it. It's a chemically active, mildly toxic, UV-charged surface that reacts to sunlight in ways that can be dangerous to biology, and every single person who eventually walks on it is going to need serious engineering between their body and that dust, not just a good pair of boots. It's worth taking a moment to appreciate just how long this particular hazard has been sitting in the data before anyone fully understood what it meant. The Viking landers picked up hints of chlorine-based compounds in the Martian soil all the way back in 1976, more than 3 decades before the Phoenix lander finally confirmed exactly what those compounds were and how much of them were actually present. For most of that gap, the Viking chlorine signal was treated as a curiosity, something scientists filed away without necessarily grasping its full significance. It took Phoenix landing directly in the Martian Arctic in 2009 and running its own chemistry experiments on freshly scooped soil to finally nail down the answer. These weren't trace contaminants. Perchlorates were a real, substantial part of the Martian soil composition, present at levels high enough to be a genuine concern rather than a footnote. And once scientists understood what they were looking at, the more they studied it, the more layered the problem turned out to be. It's not simply a matter of avoiding direct contact with the dirt, the way you might avoid touching something you know is poisonous back on Earth. Martian dust doesn't stay put. It's fine enough, and clingy enough, thanks to that electrostatic charge we already talked about, that it gets into everything. Seals, joints, air filtration systems, the folds and gaskets of a spacesuit. Apollo astronauts on the Moon already ran into a related version of this problem decades ago, discovering that lunar dust clung stubbornly to their equipment no matter how they tried to brush it away, and lunar dust doesn't carry anything close to the same chemical toxicity that Martian dust does. Combine Martian dust's chemistry with its physical clinginess, and you get a substance that isn't just dangerous if you touch the ground carelessly. It's dangerous because it actively wants to travel with you, into your habitat, into your equipment, potentially into the very air you're breathing inside a supposedly sealed environment. That's part of why the ultraviolet interaction matters so much, beyond the pure chemistry of it. Perchlorate sitting quietly in undisturbed soil is one kind of hazard. Perchlorate that's been kicked up into the air by a rover's wheels, or by wind, or by human boots walking across the surface, and then exposed to Mars's unfiltered UVB and UVC radiation on its way into a habitat's airlock system, is a more dangerous version of the same problem, because that's exactly the exposure pathway that produces those more reactive, more dangerous byproducts researchers have identified, the hypochlorite and chlorite compounds capable of killing even perchlorate-tolerant microorganisms within minutes under lab conditions. Every time dust gets disturbed on Mars, in other words, there's a chance it's being freshly activated by exactly the kind of radiation that makes it worse, right before it has a chance to work its way into an airlock, a seal, or a piece of equipment that a human being is going to be breathing near. There is a reason to end this part of the story on something other than pure alarm, though, because the same research that identified perchlorate as a serious hazard has also consistently framed it as a solvable engineering problem rather than an unsolvable one. Filtration technology already exists on Earth for dealing with perchlorate contamination, ironically because we've already had to deal with a real-world version of this exact chemistry. Chile's Atacama Desert, one of the driest and most Mars-like environments on our own planet, naturally contains significant perchlorate in its soil. For years, Atacama soil was actually harvested and used as agricultural fertilizer in the United States, before scientists discovered the perchlorate in it was leaching into groundwater supplies used for drinking water, prompting a public health response and further study into exactly how to detect and filter it. That real-world experience on Earth, dealing with an actual perchlorate contamination event in an actual water supply, has directly informed how scientists think about protecting future Mars crews from the same basic chemistry, just in a far more extreme version of the problem, on a planet where there's no backup water supply to switch to if the local processing systems fail. There's one more angle to the toxic soil story worth spending time on, because it connects directly back to something we already covered with the dust storms, and it shows just how much these hazards overlap and reinforce each other, rather than existing as neat, separate categories. Remember that Martian dust is electrostatically clingy, fine enough to work its way into equipment seals. And remember that a global dust storm can fill the entire atmosphere with that same dust for weeks or months at a time. Now layer the perchlorate chemistry on top of that picture. During a major dust storm, the amount of chemically active, UV-processed dust suspended in the air and settling onto every exposed surface would be at its absolute highest, exactly the moment when a habitat's air filtration and seal systems would be under the most stress, trying to keep that same material out. It's not that the dust storm hazard and the toxic soil hazard are two separate problems sitting on a checklist. They're the same underlying material, at different moments, creating compounding difficulty depending on what the weather happens to be doing on any given day. There's also a broader lesson buried in the mouse study we mentioned earlier that's worth drawing out a little further. That research used a soil simulant, a laboratory stand-in built to approximate real Martian regolith as closely as scientists can currently manage, at exposure doses that were, by any reasonable standard, extremely small, a fraction of a milligram in the low-dose group, a single milligram in the high-dose group, and even at those modest exposure levels, researchers found measurable lung scarring within just 7 days. Scientists studying astronaut health specifically flagged this as a pulmonary concern precisely because of how this particular hazard is different from most of the others we've covered. Radiation exposure, dangerous as it is at least something you can shield against with enough mass between you and the source. Toxic dust that's fine enough to bypass normal filtration and settle directly into lung tissue is a different kind of problem, one that depends enormously on getting the engineering of seals, airlocks, and filtration systems exactly right every single time for the entire duration of a mission that could stretch past 1,000 days. Now let's step back and talk about the environment surrounding all of this, the air itself, or what passes for air on Mars, and the temperatures that come with it. If you could somehow stand on the surface of Mars right now without any protection at all, one of the very first things that would kill you has nothing to do with radiation or toxic soil. It's the simple fact that you cannot breathe the air. The Martian atmosphere, according to figures from the European Space Agency, is made up of roughly 95.32% carbon dioxide, 2.7% nitrogen, 1.6% argon, and just 0.13% oxygen. Put together, oxygen and water vapor, the two things our lungs and our bodies rely on most directly, make up less than 0.2% of the total air. There's no version of unprotected human breathing that works in that mixture, not for more than a few seconds. And even if the composition were somehow fixable, the pressure alone would still be a death sentence. Earth's average sea level atmospheric pressure sits around 1,013 millibars. Mars's average surface pressure is somewhere around 6.35 millibars, with the number fluctuating seasonally and by elevation across a range of roughly 2 to 12 millibars, depending on where and when you're measuring. Do the comparison and you land somewhere between 100 and 170 times thinner than what we breathe here, depending on exactly which numbers you're comparing. That's not thin air, the way a mountain climber on Earth thinks of thin air. That's close enough to a vacuum that unprotected exposure would be fatal within minutes, full stop, according to the researchers who study this directly. No amount of holding your breath solves that problem. Then there's temperature, and this is where Mars starts to feel less like a single environment and more like several completely different worlds stitched together, depending on where you're standing and what time of day it is. At the extremes, surface temperatures can range from around -130 degrees Celsius, that's about -200 degrees Fahrenheit, at the winter poles, all the way up to a summer equatorial high of around 20 to 30 degrees Celsius, which is roughly 68 to 86 degrees Fahrenheit. That upper number might sound almost pleasant, almost like a mild day back home, and that's exactly the trap. It's an extreme, not a typical condition, and it exists right alongside some of the coldest temperatures found anywhere on a rocky planet's surface in our solar system. The day-to-night swing is arguably even more brutal than the seasonal extremes, because it happens every single day, over and over, without fail. At the Viking and Pathfinder landing sites, both sitting around 20 degrees north latitude, roughly comparable in latitude terms to somewhere like the Sahara or central Mexico here on Earth, researchers recorded typical daily temperatures swinging from a low near -84 degrees Celsius, about -119 Fahrenheit, right before sunrise, up to a high of around -33 degrees Celsius, about -28 Fahrenheit, in the early afternoon. That's a swing of roughly 50 degrees Celsius, happening every single day, at a location chosen specifically because it was one of the milder, more moderate places on the entire planet. According to Encyclopaedia Britannica's own summary of Martian climate research, That kind of daily temperature swing is significantly larger than anything you'd experience in even the harshest deserts here on Earth. The reason for that dramatic swing comes right back to the thin atmosphere we already talked about. On Earth, our thick blanket of air holds onto heat overnight, acting like insulation and smoothing out the difference between day and night. Mars's atmosphere is so thin that it simply can't do that job. Heat radiates away from the surface almost as fast as it arrives, which is why the ground can bake in relatively bright sunlight during the day and then plunge towards some of the coldest temperatures on the planet within a matter of hours once the sun goes down. Even the average conditions, away from the extremes, are harsh by any human standard. Researchers commonly cite an average surface temperature around -60 degrees Celsius. That's about -76 degrees Fahrenheit, with the average temperature in the lower atmosphere sitting close to 200 Kelvin, or roughly -70 degrees Celsius, about -100 degrees Fahrenheit. This isn't a planet with a bad winter and a nice summer, the way we think about seasons here. It's a planet where cold, by Earth standards, is essentially the baseline condition, and anything approaching what we'd call comfortable is a rare, narrow exception. All of this cold and low pressure together creates a strange consequence for water. Liquid water is fundamentally unstable on the Martian surface under normal conditions, according to researchers at the Royal Meteorological Society who study Martian weather patterns. Instead of melting the way ice does on Earth, water on Mars tends to transition directly between solid ice and vapor, skipping the liquid phase entirely in a process called sublimation, because the combination of low pressure and cold temperatures simply doesn't allow liquid water to exist stably out in the open for long. That's part of why, even with everything we now know about ancient rivers and lakes that once existed on this planet billions of years ago, and even with the newer discoveries about liquid water hiding deep underground that we're going to get into shortly, the surface itself, right now, today, is not a place where you'd find puddles or streams. The physics of the atmosphere simply won't allow it. And then there's the wind, which behaves in its own strange, almost contradictory way. Down at the surface, where a person would actually be standing and working, wind speeds measured by the Viking landers were, in relative terms, fairly gentle, somewhere around 2 to 7 meters per second in summer conditions, 5 to 10 meters per second in fall, climbing to somewhere around 17 to 30 meters per second during an active dust storm. But up at high altitude, in the winter jet stream that circles the planet, wind speeds can reach eastward velocities above 100 meters per second, which works out to roughly 225 miles per hour. That's an almost unbelievable contrast. Relatively mild breezes down where a person would be standing, layered underneath jet stream-level winds screaming overhead, driven by exactly the same large-scale thermal patterns that fuel the planet's dust storms in the first place. There's a seasonal pattern hiding underneath all of this weather data that's worth connecting back to the dust storms we covered earlier, because it isn't random. Dust storms on Mars, including the regional ones that sometimes grow into planet-covering events like the 2018 storm, tend to occur more frequently during the period when Mars is closest to the Sun in its elliptical orbit, the point astronomers call perihelion. That's not a coincidence. It's the same underlying thermal physics driving everything else we've talked about throughout this entire section on atmosphere and temperature. More direct sunlight means more intense heating of the bare, dark regolith on the surface, which creates stronger temperature contrasts between different regions, which in turn fuels the kind of atmospheric convection that can kick dust up off the ground and, under the right conditions, let a small regional event snowball into something that eventually swallows the entire planet. None of this makes dust storms predictable in the way weather forecasting works on Earth, but it does mean they're not simply random bad luck either. They're a structural feature of how this particular planet's climate operates, tied directly to its orbit, its axial tilt, and the same thin, unforgiving atmosphere that shapes every other hazard we've covered today. It's worth remembering, too, that Mars wasn't always like this. The same researchers studying its thin, hostile modern atmosphere have also found strong evidence that Mars once had a much thicker one, dense enough to potentially support liquid water sitting on the surface for extended stretches of time. NASA's MAVEN mission has spent years specifically studying how the solar wind, unfiltered by any global magnetic field, gradually stripped that original atmosphere away over the course of billions of years. So the version of Mars we're describing right now, the freezing nights, the near vacuum pressure, the impossible day-to-night temperature swings, isn't necessarily the planet's permanent, unchanging identity. It's what's left after billions of years of erosion at the hands of the very same sun that once, perhaps, let this world look a lot more like our own. It's worth sitting with just how strange it would feel to actually stand somewhere on Mars and watch the temperature swing the way it does. Imagine a location on Earth that gets roughly as much sunlight as somewhere near the Sahara or central Mexico, comfortably warm through the middle of the day. Now imagine that same location dropping, every single night without exception, down to temperatures colder than almost anywhere humans have ever permanently lived on Earth, and then climbing back up the next day, only to repeat the exact same brutal cycle again the following night. That's the ordinary daily rhythm at some of the more moderate latitudes on Mars, not a rare weather event, just the standard operating pattern the planet runs through every single day, driven entirely by an atmosphere too thin to hold on to any of the day's heat once the sun goes down. The pressure problem compounds all of this in a way that's easy to underestimate if you're picturing Mars as something like a very cold desert. On Earth, even in the most extreme cold, the air pressure around you stays roughly the same as it is anywhere else near sea level, which means your body doesn't have to fight against a second, entirely separate hazard on top of the temperature. On Mars, you're dealing with both problems stacked on top of each other simultaneously. Air so thin, it sits somewhere between 100 and 170 times less dense than what we're used to breathing, combined with temperatures that would freeze exposed skin in moments. Neither problem alone would be survivable without serious protection. Together, they mean that Mars offers essentially zero margin for any kind of equipment failure. A leak that might just be uncomfortable in a cold environment with normal pressure becomes catastrophic within minutes in an environment with almost no pressure at all. And then there's the deeper irony sitting underneath all of this atmospheric hostility, the fact that Mars apparently wasn't always built this way. The same MAVEN mission data that helped establish just how thin and unprotected the current Martian atmosphere is, has also helped build the case that Mars once had something dramatically different. A thicker atmosphere, substantial enough that liquid water could plausibly have sat on the surface for extended stretches of time, feeding the very rivers and lake basins that show up so clearly in orbital photography of ancient Martian terrain. Somewhere in the multi-billion-year gap between that earlier version of the planet and the version we're describing right now, cold, thin, inhospitable, the solar wind slowly, patiently stripped nearly all of that protective air away, particle by particle, over a timescale that's almost impossible for a human mind to properly hold on to. What we're describing throughout this entire section, in other words, isn't necessarily Mars's permanent, unchangeable nature. It's what happens to a planet over billions of years once it loses the one thing that was protecting its atmosphere in the first place: a functioning global magnetic field, the exact same kind of shield that's still quietly protecting every single one of us right now, every day, without most of us ever thinking about it at all. Now let's talk about what all of this does to the human body itself. Separate from radiation, separate from toxic dust, separate from cold. Because even in a perfectly sealed, perfectly heated, perfectly shielded habitat, there's one more thing about Mars working against you around the clock, and there's no engineering fix for it. It's gravity. Mars has surface gravity of about 38% of what we experience here on Earth, 0.38 g, in the shorthand researchers use. That number sounds almost like a minor footnote next to radiation doses and toxic soil. But the more scientists study it, the more it looks like a genuinely serious long-term problem for anyone planning to actually live there, not just visit briefly. Most of what we know about how reduced gravity affects the human body comes from decades of research into full weightlessness, microgravity, the kind astronauts experience aboard the International Space Station. And that research paints a pretty stark picture on its own. NASA's own human research program has documented that astronauts can lose up to roughly 1 to 1.5% of their bone mass per month in weight-bearing bones, specifically areas like the hip and the lumbar spine, during extended stays in microgravity. That bone loss happens through a two-part mechanism. The body starts breaking down bone tissue faster than normal, a process called resorption, while at the same time absorbing less calcium through the intestines than it normally would. Both effects push in the same direction, and both accelerate the longer someone stays in that environment. Muscle loss follows a similarly alarming pattern. According to a systematic review of research into spaceflight and the musculoskeletal system, astronauts in microgravity can lose up to 20% of their average skeletal muscle mass and up to 30% of their muscle strength within a single month. That's worth sitting with for a second, because skeletal muscle isn't some minor tissue type tucked away somewhere in the body. It makes up more than 40% of total human body mass. It's essentially the largest single organ system most of us never think about, and in weightlessness, it starts breaking down fast, which has real consequences not just for how someone looks or feels, but for their actual ability to perform physical tasks, whether that's a spacewalk, an equipment repair, or eventually, hard manual labor on the surface of another planet. But here's the genuinely tricky scientific problem underneath all of this. Almost every piece of that microgravity research comes from full weightlessness, essentially zero gravity, which is not what astronauts on Mars would actually be experiencing. Mars isn't weightless. It has real gravity, just less of it than Earth, at that 38% figure. And researchers studying this gap have been pretty upfront that we simply don't have much direct human data on what partial gravity, as opposed to zero gravity, actually does to the body over the long term, because no human being has ever lived for an extended period anywhere with gravity between Earth's and true weightlessness. That's exactly why researchers have turned to animal studies using centrifuges, machines that can simulate different partial gravity levels for extended periods. One study cited by researchers at the University of Rhode Island's Metabolism and Muscle Biology Lab used a centrifuge to expose test animals to a gravity level of 0.33 g, chosen specifically because it sits extremely close to Mars's actual gravity of 0.38 g. What they found offers a small sliver of encouraging news buried inside an otherwise sobering picture. Exposure to 0.33 g partially mitigated the kind of muscle atrophy typically seen in full weightlessness. It didn't prevent it entirely, but it noticeably slowed it down compared to zero gravity. Full protection against muscle atrophy in that same study only showed up at a higher gravity level, around 0.67 g, which is still meaningfully more gravity than Mars actually has. In other words, Mars's gravity might help, compared to the alternative of full weightlessness during the journey there, but the current evidence suggests it likely wouldn't be enough, on its own, to fully protect the human body the way Earth's gravity does. Researchers have tried to translate all of this into concrete predictions for what an actual crewed Mars mission would do to the people flying it, and the numbers are striking. One modeling study, published in peer-reviewed research and cited by NASA-affiliated researchers, looked at two realistic mission profiles. The first is what's called an opposition-class mission, a shorter trip lasting somewhere between 400 and 600 days total. The model predicted that 62% of astronauts on a mission of that length would develop osteopenia, meaning fully weakened bone density, with 33% falling into a range considered at risk for full osteoporosis. The second profile is a conjunction-class mission, a longer trip stretching somewhere between 1,000 and 1,200 days. For that longer mission length, the same model predicted that 100%, every single astronaut, would develop osteopenia by the end of it. Read that again slowly, because it's one of the more sobering numbers in this entire research pass. Every single crew member, on the longer and arguably more realistic version of a Mars mission, modeled to develop weakened bones as a predictable, expected outcome of simply going, doing the mission, and coming home, separate from any accident, any equipment failure, any dust storm or radiation spike. Just the baseline physiological cost of existing in reduced gravity for that length of time. Reduced gravity is also expected to affect the cardiovascular system, since the heart doesn't have to work nearly as hard to pump blood around the body when there's less gravitational pull working against it, which over time can lead to a kind of cardiovascular deconditioning. It's worth being precise about this particular point, though. This expectation is drawn largely from what researchers already understand happens during microgravity, extrapolated forward to a partial gravity environment like Mars, rather than something that's been directly measured in a genuine long-duration partial gravity setting, simply because no human mission like that has happened yet. It's an informed, physiologically reasonable expectation built on decades of related research, not a hard measurement from the actual environment in question. Put all of that together, and you get a picture where the human body itself becomes one of the central engineering problems of a Mars mission, arguably as complicated as the radiation shielding or the life support systems. It's not enough to build a habitat that keeps the air breathable and the temperature survivable. You also have to account for the fact that every single day a crew spends on Mars, their bones are quietly weakening, their muscles are quietly wasting, at rates we can estimate reasonably well from related research, but haven't yet confirmed directly, because nobody has ever actually lived there long enough for us to check. There's something worth appreciating about how researchers even attempted to study this problem in the first place, given that nobody has ever actually lived in Martian gravity. You can't simply put a human being in a partial gravity environment for months at a time here on Earth to see what happens. The technology to reliably simulate that kind of sustained partial gravity for humans over long periods essentially doesn't exist outside of extremely short-duration parabolic flights. So researchers have had to build their understanding indirectly, layering together data from actual microgravity experience on the International Space Station, mathematical models that extrapolate what partial gravity should theoretically do based on known biology, and centrifuge experiments run on smaller test animals, where scientists can at least approximate different gravity levels for extended stretches of time in a lab setting. Each of those approaches has real limitations on its own. Put together, they represent the best current understanding of a problem that, frankly, won't be fully solved until human beings actually go, and the doctors monitoring them get real data back. That gap between theoretical modeling and lived experience matters because of how much rides on getting the countermeasures right. Astronauts on the International Space Station already spend a significant portion of their daily schedule on structured resistance and cardiovascular exercise, specifically designed to slow down bone and muscle loss in microgravity. And even with that dedicated daily effort, the loss rates described earlier, up to that 1 to 1.5% of bone mass per month, up to 20% of muscle mass, and 30% of muscle strength within a single month, are what actually happens even with active countermeasures already in place. A Mars mission would need its own version of that exercise regimen, likely adapted specifically for 0.38 g rather than full weightlessness, running for the entire outbound cruise, the entire surface stay, and the entire return trip, with the added complication that nobody has direct long-duration data confirming exactly how effective any given exercise protocol actually is at that particular gravity level, because it's never been tested that way before. There's also a detail buried in the modeling research that's easy to skip past, but genuinely important for anyone thinking seriously about how a real mission would need to be planned. The predictive study on bone mineral density loss didn't just produce one alarming number and stop there. It specifically compared two different mission lengths, precisely because mission planners need to understand how the risk changes depending on how long a crew actually stays. The shorter opposition class profile, 400 to 600 days total, produced a serious but not universal risk. 62% developing osteopenia, 33% at risk for osteoporosis. The longer conjunction class profile, stretching out to 1,000 or even 1,200 days, pushed that same modeled outcome all the way to 100%. That's not a small difference in outcome for what might sound, at a planning level, like a fairly modest difference in mission architecture. It's the difference between a mission where most, but not all of the crew comes home with meaningfully weaker bones, and a mission where the model predicts literally everyone does. Decisions about exactly how a Mars mission gets structured, how long the crew actually stays on the surface before starting the trip home, aren't just budget and logistics questions. According to this research, they're direct, measurable trade-offs against the long-term skeletal health of every single person on board. The kind of trade-off that has to get weighed against everything else driving mission length, the cost of launching more supplies, the narrow windows when Earth and Mars actually line up favorably for an efficient transfer orbit, and the scientific value of a longer stay on the surface. All of it balanced against a body that starts quietly working against itself the moment gravity drops to a third of what it evolved to expect. There's a specific moment in a hypothetical Mars mission that's worth thinking through carefully, because it shows how these different hazards don't just add up, they actually collide with each other at exactly the worst possible time. Picture the moment a crew actually arrives on the Martian surface after that roughly 180-day cruise through open space. For the entire outbound journey, those astronauts have been living in a microgravity environment, the same full weightlessness that produces the most severe bone and muscle loss researchers have documented, up to that 1 to 1.5% of bone mass per month, up to 20% of muscle mass within 30 days. By the time they actually land on Mars, their bodies have already been weakened by months of exactly that kind of deconditioning. And the very first thing they have to do, immediately upon arrival, with weakened bones and wasted muscle, is transition into a gravity field that, while less demanding than Earth's, still represents a meaningfully different physical load than the zero gravity they'd been adapting to for the previous 6 months. There's no rest period built into the physics of the situation. The moment they step onto the surface, their already compromised bodies have to start bearing weight again, in an environment where researchers still don't have complete data on how well that adaptation actually goes, precisely because no human being has ever done it before. The cardiovascular piece of this fits into the same picture. In microgravity, without Earth's gravity constantly pulling blood downward toward the legs, fluid in the body tends to shift upward toward the chest and head, and the heart doesn't have to work nearly as hard to circulate blood around the body as it does under normal gravity. Over months of spaceflight, that reduced workload appears to lead to a kind of deconditioning, a heart that's grown less accustomed to working against any real gravitational resistance. Landing on Mars, even at only 38% of Earth's gravity, would immediately reintroduce a meaningful gravitational load on a cardiovascular system that spent half a year adapting to something much closer to none at all. Researchers studying this expect real physiological strain during exactly that transition period, extrapolating forward from what's already well understood about astronauts returning to full Earth gravity after long station stays, even though, again, nobody has direct data confirming precisely how that adaptation plays out at Martian gravity specifically, because the moment hasn't happened yet. Now let's zoom out from the human body entirely and look at the machines we've actually sent to Mars, because the story of how badly this planet has treated our hardware over the past 60+ years is its own kind of warning, and it comes with its own strange, half-joking name in the scientific community. People who work in this field sometimes call it the Mars curse, or the Martian curse, and there's an even more colorful nickname that's floated around for decades: the Great Galactic Ghoul, a tongue-in-cheek reference to some imaginary space monster that supposedly subsists on a diet of Mars probes. Nobody actually believes there's a monster out there eating spacecraft, obviously, but the nickname stuck because, for a long time, the failure rate really was that bad, consistently, across multiple countries and multiple decades of attempts. Different sources land on slightly different numbers depending on how exactly they define failure and which time period they're measuring. But the overall pattern is consistent no matter which specific figure you look at. One broad historical overview puts the total failure rate across every country's Mars missions at around 60%, meaning roughly 6 out of every 10 spacecraft ever sent toward Mars failed in some way before completing their intended mission. A separate analysis, focused specifically on the United States and NASA's own track record, found a somewhat better success rate: 20 missions flown, 6 of them lost, which works out to about 70% success. That same analysis noted that the Soviet Union and later Russia had a dramatically worse record by comparison, with far more of their missions ending in failure. A third source describes the historical picture more loosely, calling it roughly half of all missions failing, without pinning down one exact universal percentage. The precise number moves around depending on exactly how you count it, but the underlying story doesn't. For most of the history of Mars exploration, sending something there and having it actually work was closer to a coin flip than a sure thing. It all started in 1960, when the Soviet Union made humanity's very first attempt to reach Mars. It failed, setting the tone, in a way, for the decades that followed. But it's worth understanding why these missions failed so often, because the reasons range from wildly unlucky mechanical failures to genuinely embarrassing human mistakes, and both categories tell you something important about just how unforgiving this kind of interplanetary engineering actually is. Take NASA's Mars Observer, lost in 1993. This spacecraft had made it almost the entire way there, 337 days into its journey, just 3 days away from the critical moment when it needed to fire its engines and settle into orbit around Mars. And then, silence. The leading explanation is that while pressurizing its fuel tanks in preparation for that orbital insertion maneuver, the propulsion system developed a leak, releasing fuel and gas in a way that sent the spacecraft into an uncontrolled spin, which triggered its electronics to switch into a defensive safe mode. There was never any further communication after that. A machine that had successfully survived the entire journey through interplanetary space, 337 days of travel, was lost in the final 72 hours before it would have reached its destination. Then there's the Mars Climate Orbiter, and this one has become something close to a legend in engineering circles, not because of some exotic mechanical failure, but because of an almost absurdly simple human mistake. The Mars Climate Orbiter launched on December 11, 1998, designed to study the Martian climate and atmosphere and to serve as a communications relay for a companion mission, the Mars Polar Lander, which was scheduled to land shortly afterward. Everything about the mission's long journey through space went fine. Then, on September 23, 1999, as the spacecraft approached Mars for its critical orbital insertion, contact was permanently lost. The investigation that followed uncovered the cause, and it's the kind of mistake that sounds almost too simple to have destroyed a multi-hundred-million-dollar spacecraft. The ground navigation software, running at NASA's Jet Propulsion Laboratory, was built to work in metric units, calculating thruster force in newtons, the standard scientific unit for force. But the spacecraft itself had been built by Lockheed Martin, and the acceleration and thruster data the company's engineers provided during development had been calculated in pound force, the old imperial unit still commonly used in American engineering. Nobody caught the mismatch. The navigation team was feeding numbers calculated in one unit system into software, expecting an entirely different unit system, and the resulting trajectory errors compounded quietly over the entire mission, until the spacecraft arrived at Mars on a path that brought it roughly 100 kilometers lower than its intended altitude of 150 kilometers above the surface. At that altitude, atmospheric friction and heating destroyed the spacecraft. The full mission, covering both the orbiter and its companion lander, had cost $327.6 million, which works out to roughly $586 million in 2024 money once you adjust for inflation. All of it lost because of a units conversion error that nobody double-checked before it was too late. And the bad news for that particular mission season didn't even stop there. About 2.5 months after the Climate Orbiter failure, its companion mission, the Mars Polar Lander, was lost too, crashing into the Martian surface during its own landing attempt. This one didn't share the exact same cause as the Climate Orbiter's failure, but investigators pointed to a common thread running underneath both losses: inadequate funding and mission management pressures tied to NASA's guiding philosophy at the time, an approach informally known inside the agency as faster, yupser, cheaper. That doctrine, adopted under NASA leadership in the 1990s, pushed for smaller, less expensive spacecraft launched more frequently, moving away from the older approach of building enormous, heavily instrumented probes that took years and enormous budgets to develop. The philosophy had real benefits in terms of mission cadence, but the back-to-back losses of the Climate Orbiter and Polar Lander became one of the clearest illustrations of what can go wrong when cost pressure runs up against the extraordinarily unforgiving margin for error that interplanetary navigation actually requires. The Soviet Union's own history with Mars is arguably even rougher. In 1988, they launched twin probes named Phobos 1 and Phobos 2, aimed at studying Mars and specifically its larger moon, Phobos. Phobos 1 operated normally right up until an expected communications session on September 2, 1988, simply failed to happen. Investigators eventually traced the cause back to a software error, one that deactivated the spacecraft's attitude control thrusters. Without those thrusters working correctly, the spacecraft's solar panels drifted out of alignment with the sun, its batteries slowly drained with nothing recharging them, and the mission died quietly, before it had even reached its destination. Phobos 2 fared better, at least initially. successfully reaching Mars orbit on January 29, 1989, and gathering real data on the Sun, the interplanetary environment, and Mars itself during its approach. But it too failed, before completing its full mission, going silent shortly before it was scheduled to release landers down onto the surface of Phobos itself. Russia's more modern attempt didn't go any better. In November of 2011, Roscosmos launched a mission called Phobos Grunt, an ambitious plan to land on Phobos, collect a physical sample, and bring it back to Earth, while also carrying China's Yinghuo 1 probe along for the ride to place it into Mars orbit. The mission suffered a complete control and communications failure almost immediately after launch. It never even left Earth orbit successfully, and it eventually fell back down through the atmosphere, ending the mission before it had traveled anywhere close to Mars at all. Even the successes in this story came with their own dramatic complications. Mariner 9 achieved something genuinely historic in 1971, becoming the very first spacecraft from any nation to successfully enter orbit around another planet. But when it arrived, it found the entire planet wrapped in a massive dust storm, exactly the kind of planet-wide event we already talked about with Opportunity decades later, except this time it greeted the first spacecraft ever to arrive in Mars orbit. Two Soviet orbiters, Mars 2 and Mars 3, reached the planet around the same time and ran into the identical storm. Rather than treating the situation as a total loss, the Mariner 9 team made a clever adjustment. While they waited for the storm to clear enough to actually photograph the surface in useful detail, they redirected the spacecraft to study and photograph Phobos instead, turning unplanned downtime into a small scientific bonus. Once the storm finally did clear, the images Mariner 9 sent back represented a massive leap forward over anything previous missions had captured, and among the details visible in that clearer view were the first strong pieces of evidence suggesting liquid water might once have flowed across the Martian surface, a discovery that would go on to shape decades of research that followed. It's important to say clearly that this is not the whole story anymore. Mission success rates have improved dramatically since roughly the year 2000, and the string of missions that followed those early decades of the Mars curse tells a genuinely different story. The twin Viking landers in 1976 pulled off a full success. Mars Pathfinder landed successfully in July of 1997, carrying the small Sojourner rover along with it. Spirit and Opportunity both touched down successfully in January of 2004, with Opportunity going on, as we already covered, to outlast its planned lifespan by a factor of 60. And Perseverance, along with the small Ingenuity helicopter that flew alongside it, landed successfully in February of 2021. Most missions launched by NASA and other space agencies in the 21st century have succeeded, a sharp turnaround from the coin flip odds of the earlier decades. It's worth actually sitting with that list of successes for a moment, rather than just rushing past it, because each one of those missions represents its own small miracle of engineering, built directly on top of the lessons paid for by the failures that came before it. The Viking landers in 1976 weren't just the first American spacecraft to successfully operate on the Martian surface. They were the missions that first detected those perchlorate signals decades before anyone fully understood what they were looking at, laying the groundwork for research that wouldn't be fully resolved until Phoenix confirmed it more than 30 years later. Mars Pathfinder, arriving in July of 1997 with the small Sojourner rover riding along, proved out an entirely new landing approach using airbags to cushion the impact, a technique that would go on to be reused for Spirit and Opportunity's landings in January of 2004. Phoenix, touching down in the Martian Arctic in 2008, brought real chemistry experiments directly to the soil for the first time, giving scientists the confirmation they needed about perchlorate concentrations, rather than relying on decades-old, indirect Viking-era hints. Curiosity's landing in August of 2012 involved one of the most audacious pieces of engineering ever attempted on another planet, a system nicknamed the Sky Crane, which lowered the rover gently onto the surface on cables from a hovering rocket-powered platform, an approach so unusual that mission engineers themselves described the entire 7-minute descent sequence as nerve-wracking territory, precisely because so much of it had never been tried before and had to work perfectly, autonomously. with no chance for a human hand to step in if something went wrong. It worked, and it's been running the RAD instrument ever since, giving us the entire radiation dataset this video opened with. InSight's 2018 landing brought something different again. Not a rover built to explore laterally across the surface, but a stationary lander built to listen, patiently, to the planet's interior. A mission whose real payoff wouldn't fully arrive until years after the mission itself had already ended, when researchers went back through its recorded seismic data and found evidence of liquid water hiding kilometers below where InSight had been sitting the entire time. And Perseverance, landing in February of 2021 alongside the Ingenuity helicopter, represents the most recent chapter in a story that keeps building on everything that came before it. One hard-won engineering lesson at a time, one successful landing at a time, gradually turning what was once closer to a coin flip into something approaching, though never quite reaching, a routine operation. But the reason engineers still bring up the Mars curse, even now, even after this long run of successes, is that the underlying difficulty never actually went away. It's just being managed better. Every single one of these missions still has to execute an entirely autonomous entry, descent, and landing sequence once it reaches Mars, because the communication delay between Earth and Mars, which can stretch to over 20 minutes one way depending on the planet's relative positions, makes real-time human control physically impossible. There's no joystick, no last-second correction from mission control. The spacecraft has to fly itself through a sequence lasting only a few minutes, hitting the atmosphere at enormous speed, deploying parachutes in an atmosphere too thin for parachutes alone to do the job properly, firing retro-rockets, and touching down, all without a single human being able to intervene if something goes wrong. 60-plus years of history, and dozens of missions from multiple countries, have made it very clear that this remains one of the hardest engineering problems humanity has ever taken on, regardless of how much better our success rate has gotten. It's a problem that doesn't fully go away just because a team has succeeded before, either. Every single landing, no matter how many that specific space agency has already pulled off successfully, still has to execute that same unforgiving, fully autonomous sequence against the same thin atmosphere, the same communication delay, and the same total absence of any second chances if something goes wrong in those final few minutes. That's part of why, even now, even with a run of successes stretching back more than 2 decades, mission teams still describe the moments around a Mars landing with the same tension every single time, because on some level, they know exactly how many things had to go right, and exactly how little room there ever was for anything to go wrong. It's worth dwelling for a moment on just how unforgiving the physics of actually landing on Mars really is, because it explains why the failure rate stayed so stubbornly high for so long, even among space agencies with enormous budgets and genuinely brilliant engineering teams behind them. Mars occupies this strange, uncomfortable middle ground that makes landing there harder, in some ways, than landing almost anywhere else in the solar system. Its atmosphere is thick enough to generate serious heating during atmospheric entry, the same kind of friction and heat buildup a spacecraft would experience entering Earth's atmosphere, which means a heat shield is absolutely necessary. But that same atmosphere is simultaneously too thin to let parachutes alone do the job of slowing a heavy spacecraft down to a safe landing speed, the way parachutes can on Earth. So every single successful landing has needed some additional combination of retro-rockets, airbags, or increasingly complex descent systems layered on top of the parachutes. Each new piece of hardware representing another opportunity for something to go wrong, executed in a matter of minutes, entirely without human oversight, because of that communication delay stretching up to 20 minutes each way. Engineers who've worked on these missions have a name for that entire sequence: entry, descent, and landing, often shortened to EDL, and it's frequently described within the space industry as among the most stressful few minutes in all of aerospace engineering, precisely because of how little room there is for anything to go wrong and how impossible it is for a human being on Earth to step in and fix a problem in real time once it starts. A spacecraft entering the Martian atmosphere is traveling at enormous speed, and within a span of minutes, it has to slow down dramatically, deploy a heat shield, deploy a parachute, potentially fire retro rockets, and touch down gently enough not to destroy the very equipment it just spent months or years carrying safely across interplanetary space. Every part of that sequence has to work correctly, in the right order, at the right moment, without a single human hand able to intervene. Because by the time a warning signal could travel back to Earth and a correction could be sent back to Mars, the entire landing sequence would already be over, one way or the other. Given that reality, it starts to make a lot more sense why the earliest decades of Mars exploration produced such a rough track record, and why the improvement since roughly 2000 represents such a genuinely significant engineering achievement rather than just good luck. Each failure, painful as it clearly was for the teams involved, fed directly into the next generation of missions. The metric versus imperial units failure that doomed the Mars Climate Orbiter led directly to stricter cross-checking procedures across NASA's engineering teams, procedures that persist to this day, specifically because of that one expensive, humbling lesson. The propulsion failure that likely doomed Mars Observer fed into how future spacecraft handle fuel pressurization procedures. Even the dust storm that ultimately killed Mariner 9's original photography plans in 1971 taught mission planners something valuable about building flexibility into a spacecraft's schedule, since the team's decision to redirect toward photographing Phobos while waiting out that storm turned unplanned downtime into real scientific value instead of simply wasted time. Bit by bit, mission by mission, often at the cost of hundreds of millions of dollars and years of a team's work, this accumulated, hard-won experience is a huge part of why missions like Curiosity, Insight, and Perseverance have been able to land successfully in the more recent era, building directly on lessons that were often paid for by earlier, very public failures. Which brings us, finally, to the part of this story that flips almost everything we've talked about on its head, at least a little. Because after all of this, after the radiation and the dust storms and the toxic soil and the crushing gravity problem and 60 years of spacecraft failures, it turns out Mars might be hiding something underneath all that hostility that changes the entire conversation. Water. We've actually known for a while that Mars had water once. More than 3 billion years ago, during geological periods scientists call the Noachian and the Hesperian, stretching roughly from 4.1 billion years ago to about 3 billion years ago, Mars appears to have had real, substantial liquid water on its surface. Rivers are believed to have carved valleys that are still visible in orbital photography today. Lakes may have existed in low-lying basins. This isn't new or controversial information. It's been building for decades, ever since missions like Mariner 9 first spotted geological features that looked unmistakably like the work of flowing water. What's new is the growing evidence for where a huge portion of that ancient water actually went. In 2025, a study published in the journal National Science Review, led by researchers including Dr. Weijia Sun at the Institute of Geology and Geophysics at the Chinese Academy of Sciences, used seismic data collected by NASA's InSight lander to identify something remarkable hiding underneath the surface. InSight had spent years listening to Mars using an extremely sensitive seismometer, picking up Marsquakes, meteorite impacts, and other seismic activity, and using the way those seismic waves traveled through the planet to map its internal structure, the same basic technique geologists use to study the inside of the Earth. Sun and the research team focused specifically on data from 3 particular events. 2 meteorite impacts recorded in 2021, given the technical designations S1000A and S1094B, and a significant Marsquake recorded in 2022, designated S1222A. What they found was a layer in the Martian crust, sitting between roughly 5.4 and 8 kilometers below the surface, where seismic shear waves consistently slowed down. That kind of slowdown is a telltale sign to seismologists, indicating a layer of highly porous rock that's saturated with something, and in this case, the interpretation the researchers landed on is liquid water, essentially an underground reservoir functioning something like an aquifer here on Earth. Porous rock, soaked through the way a sponge holds water. The scale of what they calculated is genuinely hard to picture. According to the research team's estimates, this reservoir alone could hold enough liquid water to cover the entire surface of Mars in a global ocean somewhere between 520 and 780 meters deep. Co-author Dr. Hrvoje Tkalčić from the Australian National University described the stakes of the discovery in a way that goes beyond pure geology. The water, he said, involves profound questions about life and humanity's future on the red planet. That's not a throwaway line from a press release. It's a working scientist, someone who spent years analyzing seismic data to reach this conclusion, framing the discovery explicitly in terms of what it could mean, eventually, for actual human beings trying to live there. And this isn't the only water discovery to emerge from Mars research recently. A separate study, using different InSight data and referenced through reporting that cites researchers Vashan Wright and Michael Manga, found evidence of what appears to be an even deeper reservoir, sitting somewhere between 11.5 and 20 kilometers below the surface, described as containing even more water than scientists believe once filled Mars's ancient surface oceans. But this particular reservoir comes with an important, deflating asterisk attached to it. It's not remotely accessible with any drilling technology we currently have. Even on Earth, drilling a hole a single kilometer deep is already a serious technical challenge. Drilling more than 10 times that depth on another planet with equipment that would somehow need to survive the journey there and then function reliably in that environment isn't something within reach anytime soon. So this deeper reservoir tells us something genuinely important about where Mars's ancient water actually ended up, filling in one of the biggest open questions in Martian science. But it doesn't currently represent something a future human settlement could realistically tap into for drinking water or fuel production. There's a third piece of this puzzle that's arguably the most intriguing of all, because unlike the deep reservoirs, it points towards something that might still be actively happening right now, close to the surface, rather than being locked away as ancient, inaccessible history. A more recent study, published in Nature Communications, examined what researchers call seasonal Marsquakes, seismic events whose frequency and pattern seem to shift depending on the time of the Martian year. The researchers found evidence suggesting the presence of near-surface brine, meaning salty liquid water, at shallow, meter-scale depths in parts of Mars's northern hemisphere, generally north of about 30 degrees latitude. Their working explanation ties directly back to the seasons. As ice near the surface warms during certain parts of the Martian year, it appears to transition into brine, and that seasonal ice-to-brine shift seems to increase pressure within underground pores and effectively lubricate geological faults, which in turn appears to trigger the Marsquake activity the researchers were tracking in the first place. It's important to be precise about what this study is and isn't claiming, though. The researchers themselves describe this potential brine as spatially localized, meaning confined to specific regions, rather than something spread evenly across the planet. It's not evidence of hidden lakes everywhere under the northern hemisphere. It's evidence, in specific places, of a seasonal process that might be moving small amounts of liquid water around, right now, in the modern Martian environment, rather than something that only happened billions of years in the past. Stack all three of these findings together. The shallow crustal reservoir, potentially large enough to flood the entire planet in an ocean over half a kilometer deep, the even larger but functionally unreachable deep reservoir, and the possible seasonal near-surface brine activity, and you start to see why this research has generated so much attention across 2025 and into 2026. It's worth being honest about the limits of what's actually been proven here, though, because that's part of doing this topic justice. These are seismic inferences, not direct physical samples. Nobody has drilled down, pulled up a sample of this material, and confirmed under a microscope that it's exactly what the models suggest. The researchers behind these papers are careful, in their own published language, to describe the extent of any usable water reservoir as still poorly constrained, meaning there's real, acknowledged uncertainty in exactly how much water is down there and precisely what form it's in. This is genuinely exciting, actively developing science, not a settled, closed case. And there's a bigger irony sitting underneath all of it that's worth pausing on before we wrap this up. For 6 decades, everything we've learned about Mars has painted a picture of a planet actively working against the idea of humans ever living there. Radiation levels that eat away at a career's worth of safe exposure in a matter of years. Storms that can blot out the sun across the entire planet at once, and have already killed one of our most successful machines. Soil laced with chemicals, that are actively toxic to the human thyroid and become even more dangerous once sunlight hits them. Temperature swings that would be lethal within minutes, without serious engineering standing between a person and the open air. And gravity, so different from our own, that models predict every single astronaut on a longer mission would develop weakened bones as a simple, predictable cost of going there and doing the job. And now, running right alongside all of that grim data, sits mounting evidence that this same hostile, punishing planet might be quietly sitting on more liquid water than anyone expected to find. Some of it possibly still active today, seasonally, right now, in specific corners of the northern hemisphere. Mars isn't simply hostile. It's hostile, and somehow, still holding on to exactly the resource that any future human presence there would need most. It's worth understanding exactly how these researchers actually pulled information about something as specific as underground water out of nothing more than vibrations traveling through rock, because the method itself is almost as remarkable as what it found. When a meteorite slams into Mars, or when the planet's crust shifts and produces a Marsquake, the impact sends seismic waves rippling outward through the ground in every direction. The same basic physical phenomenon that happens on Earth every time there's an earthquake somewhere on our own planet. InSight's seismometer, sitting quietly on the Martian surface, was sensitive enough to detect those waves after they had traveled through kilometers of Martian crust, and by studying exactly how those waves changed speed and shape along the way, essentially the seismic equivalent of listening to how an echo bounces differently through a room, depending on what's inside it, researchers were able to reconstruct what kind of material the waves had actually passed through. A layer of solid dry rock produces one kind of seismic signature. A layer of porous, water-saturated rock produces a distinctly different one, because water changes how efficiently certain kinds of seismic waves, specifically the shear waves the researchers focused on, are able to travel. When Dr. Sun's team calculated what are called receiver functions for these three specific events, essentially detailed profiles of how the waves bounced and reverberated as they moved through different layers of the crust, the water-saturated interpretation was what best explained the data they were seeing. It's genuinely remarkable, when you think about it, that this entire line of discovery depended on random, essentially unplannable events. Nobody scheduled those two meteorite impacts in 2021. Nobody scheduled the Marsquake in 2022. These were natural, unpredictable events happening on their own timeline, and it was only because InSight happened to be sitting there, patiently listening, with its seismometer already running, that scientists years later were able to go back through the recorded data and extract this discovery from it. InSight's own mission had already ended by the time this particular 2025 paper was published, which means the entire foundation of this discovery, about a possible underground ocean's worth of water, rests on data that had already been sitting, quietly recorded and waiting, for years before anyone fully understood what it was actually revealing. That's a detail worth appreciating on its own. Sometimes the biggest discoveries about another planet aren't made in the dramatic moment a spacecraft lands, or a new instrument switches on for the first time. Sometimes they're made years later, by a research team combing back through an archive of old data with fresh eyes, fresh methods, and a new question they didn't even know to ask the first time around. And it's worth being honest about how differently these three separate water findings actually rank in terms of practical usefulness, because lumping them together as one single triumphant discovery would blur an important distinction. The shallow reservoir, sitting between 5.4 and 8 kilometers down, is deep, certainly not something you could dig to with a shovel, but it's within a range that future drilling technology, developed specifically for Mars over the coming decades, might plausibly be able to reach. The deeper reservoir, sitting between 11.5 and 20 kilometers down, is described by the researchers who found it in far more resigned terms, openly discussed as essentially inaccessible with any technology currently available or realistically on the horizon. And the possible near-surface brine tied to seasonal Marsquakes is the shallowest of all, at meter-scale depths. But the researchers behind that particular study were careful to describe it as spatially localized rather than widespread, meaning it's not something you could count on finding just by digging in a random spot in the northern hemisphere. Three genuinely exciting findings, published within roughly a year of each other, and three very different practical outlooks hiding underneath the same broad, exciting headline about water on Mars. There's also a scientific motivation behind all of this that goes beyond simply planning for future human missions, one that researchers themselves keep returning to in how they talk about the discovery. Any region of Mars where liquid water might still exist today, even in a small, localized pocket, immediately becomes one of the most interesting places in the entire solar system to search for signs of life, whether that's ancient, long-dead microbial life preserved in the rock, or, in the most tantalizing scenario researchers allow themselves to consider, something that might still be active today. That's part of why the near-surface brine research carries a weight that goes well beyond its modest, localized scope, and part of why it's generated so much discussion among scientists who don't otherwise work directly on seismology at all. It's not simply a geology story about where ancient water went. It's a habitability story, a live, ongoing question about whether the most basic ingredient life as we understand it seems to require might still be quietly present, in specific pockets, on a planet we've spent 60 years cataloging every possible reason it shouldn't be able to support anything at all. Before we pull all of this together, it's worth taking stock of exactly where things actually stand right now, because this is very much a live, ongoing story rather than a closed chapter. Right now, there are two working rovers still active on the surface of Mars, Curiosity and Perseverance, both still sending back data, still adding to the exact same kind of measured, ground truth record that every fact in this video has been built from. Curiosity has been running continuously since its landing in August of 2012, which means the RAD instrument we spent so much time talking about at the start of this video has now been quietly logging radiation data for well over a decade, an extraordinary long-term dataset that simply didn't exist before this mission made it possible. Perseverance, which landed in February of 2021 alongside the small Ingenuity helicopter, has been building its own record ever since, adding new data with every sol that passes. As for when human beings might actually follow all of this robotic groundwork and set foot on the planet themselves, the honest answer is that there isn't a confirmed, locked-in date. You'll sometimes see references in industry and scientific commentary to the 2030s as a general target window, and NASA's own long-term planning documents have referenced ambitions in that same rough timeframe, but that's best understood as an aspirational target rather than a scheduled, guaranteed mission the way a rover launch date might be. Space agencies have a long history of ambitious timelines shifting as engineering realities, funding decisions, and new discoveries reshape what a realistic mission plan actually looks like. And everything we've covered in this video, the radiation limits, the bone density models, the questions around exactly how deep any usable water might actually sit, is precisely the kind of research that ends up directly shaping how those timelines eventually get set. What's genuinely striking, looking at the pace of discovery just over the past couple of years, is how quickly new information keeps reshaping the picture. The shallow water reservoir findings, the deeper reservoir findings, and the seasonal near-surface brine research we just walked through were all published within a tight window of each other, in 2025 and into 2026, all building on seismic data that had, in some cases, been sitting recorded and waiting for years before researchers found the right method to properly interpret it. That's not a coincidence so much as a sign of where Mars science actually is right now, a field where the raw data collection phase, landers, rovers, orbiters, physically gathering measurements, has been running for over a decade in some cases, while the analysis and interpretation of that data is still very much catching up, still producing genuinely new, headline-worthy findings on a regular basis. Which means, realistically, some of what we've covered in this video may already look slightly different by the time you're watching it, simply because that's how active this particular area of science currently is. If there's one thing the last few years of Mars research have made clear, it's that this planet still has a lot left to reveal, and the people studying it are nowhere close to running out of new questions to ask. So where does all of this actually leave us? Not with a simple, clean verdict, because the honest answer is that the science itself doesn't offer one yet. On one side, you have the people directly running the instruments gathering this data, people like Don Hassler at the Radiation Assessment Detector Team, describing the mission-length radiation dose as certainly a manageable number, something engineers can plan around, rather than something that rules the whole endeavor out. On the other side, you have researchers in the same broader field describing radiation as one of the most limiting factors standing in the way of Mars exploration, full stop. Both of those framings are showing up in the actual published research and reporting, and the difference between them often comes down to which specific safety standard you're measuring against. NASA's stricter 3% cancer risk threshold, or ESA's somewhat more permissive 1 sievert career limit. Reasonable, well-informed people looking at the exact same numbers are landing in genuinely different places, and that tension is worth sitting with rather than smoothing over. The same kind of split shows up with the toxic soil. Perchlorates are described, accurately, as a serious chemical hazard, something that demands real caution around thyroid health and lung exposure, backed up by direct quotes from the scientists who found the stuff in the first place. And at the very same time, that exact same chemical compound is being seriously studied as a potential resource, a possible source of extractable oxygen for future settlers, which means the most hostile substance on the Martian surface might also turn out to be part of the eventual solution to living there. Even the historical mission failure numbers refuse to sit still. Different, credible sources land anywhere from roughly 50 to 60% overall historical failure, depending on exactly how failure gets defined and which time window gets analyzed, while NASA's own specific track record looks notably better than the global average, closer to 70% success. There isn't one single correct number here to memorize, just a consistent underlying pattern. This has always been, and in many ways remains, one of the hardest technical challenges humanity has ever chosen to take on voluntarily. It's worth pulling together, one more time, everything this planet has actually thrown at the hardware and the handful of instruments we've managed to land there, because when you list it all out in one place, back to back, the scale of it is genuinely hard to process. A radiation environment that uses up almost an entire career's worth of safe exposure in a single round trip. A dust storm capable of turning day into night across an entire planet at once, fast enough to go from a minor regional disturbance to total global coverage in about 3 weeks, and capable of ending the mission of a machine that had already proven itself 60 times more durable than anyone expected. Soil laced with a chemical compound present at concentrations high enough to be described by the scientist who confirmed it as, in his own words, a huge amount, a compound that becomes measurably more dangerous the moment ultraviolet light touches it. An atmosphere so thin that the difference between 100 times and 170 times less dense than what we breathe barely even matters, because both numbers describe something functionally equivalent to open vacuum for a human body. Temperature swings of roughly 50 degrees Celsius between night and day, every single day, even at the more moderate latitudes chosen specifically because they were considered survivable landing zones. A gravity field weak enough that models predict every single astronaut on a longer mission will develop measurably weakened bones as a simple, expected cost of going. And a track record of spacecraft failure so consistent across 6 decades and multiple competing space programs that engineers gave it its own nickname, half joking, half not. Any one of those 7 problems, taken entirely on its own and studied in isolation, the way a single research team might spend an entire career studying just one of them, would already represent a serious engineering challenge, worthy of its own dedicated video, its own dedicated research program, its own dedicated line of funding inside a space agency's budget. Taken together, stacked on top of each other, all operating simultaneously on the same small, distant world, they represent something closer to a systems problem than a single hazard to solve. You can't fully solve the radiation question without thinking about how the shielding you add affects mission mass and cost. You can't fully solve the dust storm question without thinking about how much backup power a habitat needs to survive months without reliable sunlight. You can't fully solve the toxic soil question without building filtration systems robust enough to handle a substance that actively wants to work its way past your defenses. Every solution to one piece of this puzzle interacts with and complicates the solutions to every other piece, which is exactly why the people working on this problem professionally tend to talk about it less like a checklist to work through one item at a time, and more like a single, interconnected system that has to be designed all at once, with every decision about shielding, power, filtration, and mission length pulling against every other decision at the same time. And yet, sitting underneath every single one of those 7 hazards, in a layer of crust we only properly identified in 2025, using seismic data from a lander that had already finished its mission years earlier, might be enough liquid water to cover the entire hostile, punishing surface of this planet in an ocean over 1/2 kilometer deep. That's the detail that keeps this from being a simple story about a planet we should give up on. It's not that the danger isn't real. Every single number in this video came directly from instruments that were actually there, measuring the real thing, not from speculation or worst-case modeling dreamed up by someone who's never left Earth. But real danger and real opportunity are sitting right next to each other in the data, in a way that doesn't resolve into a clean, simple headline, no matter how many times you go back through the research. What we can say with real confidence, gathered directly from instruments that have actually been there, is this. Mars is colder, thinner, more radioactive, more chemically hostile, and more physically punishing to the human body than almost any environment human beings have ever seriously tried to live in. Every single one of those 7 hazards, the radiation, the dust storms, the toxic soil, the temperature swings, the crushing effect of low gravity on bones and muscle, and the 60-year history of hardware failures, has been directly measured, not estimated or imagined, by real spacecraft standing on real Martian ground or orbiting overhead, sending the data back across tens of millions of miles for scientists here on Earth to study, verify, argue over, and eventually build the next mission on top of. And at the same time, buried underneath every single one of those hazards, in a layer of crust between 5 and 8 kilometers down, in seasonal brine, possibly moving through faults in the northern hemisphere right now, might be the exact resource that turns this from an impossible destination into merely an extraordinarily difficult one. That's really what this whole story comes down to. Not a planet that's simply, flatly uninhabitable, and not some easy, glossy fantasy of a second Earth waiting for us either. Something stranger and more interesting than either of those extremes. A planet actively working against every part of the human body, in ways we're only now measuring with real precision, that might also, somewhere underneath all of that hostility, be holding on to exactly what we'd need to eventually make it work anyway. We went into this expecting a story about a red, dusty, mostly empty planet. What the data actually shows is a world that's radioactive in ways low Earth orbit already warned us about, that can blot out its own sun across its entire surface for months at a time, whose very soil turns actively dangerous the moment sunlight touches it, whose gravity quietly reshapes the human skeleton over the course of a single mission, and whose 60-year history of visitors from Earth reads like a genuine cautionary tale about how unforgiving interplanetary engineering can be. And running underneath every bit of that hostility, this same planet may be sitting on enough water to cover its entire surface in an ocean more than 1/2 kilometer deep. That's why Mars may be more hostile than we imagined. And it's also, strangely, exactly why so many scientists still can't stop looking at it. It's worth ending on the same note the researchers themselves keep returning to across all of this material, because it says something honest about where the science actually stands. Don Hassler, describing the mission radiation dose as manageable. Peter Smith, warning that anyone talking about living on the Martian surface had better have a real plan for dealing with the poisons in the soil. Hrvoje Tkalčić, framing the underground water discovery in terms of profound questions about humanity's future on the planet. None of these are the words of people trying to sell you a fantasy, and none of them are the words of people trying to talk you out of ever looking up at Mars again either. They're the words of scientists who've spent years, in some cases decades, working directly with the instruments and the data we've walked through today. And what comes through in their own language, over and over, is something closer to careful, clear-eyed respect for exactly how difficult this problem actually is, paired with genuine, ongoing curiosity about what still might be possible. That combination, difficulty and curiosity sitting side by side, is really the honest note to end this on. Every fact in this video came from an instrument that was actually there. RAD, sitting on Curiosity's deck since 2012, quietly logging radiation day after day. The cameras and sensors aboard the Mars Reconnaissance Orbiter watching a regional dust cloud on May 30th, 2018, grow into something that would cover an entire planet within 3 weeks. The chemistry experiments Phoenix ran directly on scooped Martian soil in 2009, finally answering a question Viking had first hinted at back in 1976. The seismometer InSight carried to the surface in 2018, listening patiently for years, recording vibrations from a Marsquake and 2 meteorite impacts that nobody could have scheduled in advance. Data that would go on, years after InSight's own mission had already ended, to reveal a possible ocean's worth of water hiding in the crust below. None of this is guesswork. It's the accumulated result of 6 decades of machines, some of them successful beyond anyone's wildest expectations, some of them lost in ways ranging from unlucky mechanical failures to embarrassingly simple human error, all of it adding up to the most complete, most measured picture of another planet's surface that humanity has ever assembled. And that's really the story underneath the story here. Mars was never going to reveal itself to us through telescopes alone, no matter how good those telescopes got. It took 60 years of trying, failing, learning, and trying again, sending increasingly sophisticated hardware across tens of millions of miles of open space to build the picture we now have. A planet more hostile, in more specific, measurable ways than almost anyone imagined when this whole effort started back in 1960, and at the exact same time, a planet that keeps giving researchers new reasons to keep looking, right up through the most recent data reviewed for this very video. Whatever comes next in this story, whether that's a confirmed date for the first crewed mission, a rover finally drilling deep enough to sample that shallow water reservoir directly, or some entirely new discovery nobody's anticipated yet, it's going to be built the exact same way everything we've covered today was built. One measurement, one mission, one hard-won piece of real data at a time, gathered by machines that had to survive exactly the same radiation, the same dust, the same toxic soil, the same cold, and the same unforgiving gravity we've spent this entire video walking through together. Thanks for watching this one all the way through, start to finish. If you want more deep dives like this, breaking down exactly what the data actually says, instead of just the highlight reel, make sure you're subscribed, and let me know in the comments what you'd want covered next, because your suggestions genuinely shape what gets researched and built into future videos on this channel.